Lesson 5 of rates of change, we're going to examine differentials in the form of dy dx equals fx gy. That means we're going to have to solve first order differential equations in that form, using a technique called the separation of variables. Let's have a bit of review first. Up until this point, we have solved differentials in the form dy dx equals something like -4 cos 3x, which is just in terms of x. We can integrate both sides with terms of x and gain a general solution. In other equations or differential equations, we've had dy dx equals y cubed take 4, where our variable is y. We've usually had to write the reciprocal or flip and then rearrange both sides before we integrate it. In this section, we'll examine differentials containing variables x and y. What do those look like? We might have an equation that's dy dx. We have 5x plus 1 over y squared plus 7. In that case, we both have variables x and y in the equation. Or this one, we have x sine y dy dx equals 2 take cos y, which means we'll need to rearrange and separate the variables. Separable equations. A separable equation is a first-order differential equation. The expression for dy dx can be factored as a function of x times a function of y. This is written as dy dx equals fx multiplied by gy. It is possible to express the right-hand side into a function of x and a function of y. So if we divide both sides by gy, it will yield the following. So we have 1 over gy, dy dx equals fx. If we integrate both sides with respect to x, it'll look like this. The integral of 1 over gy dy dx with respect to x equals the integral of fx with respect to x. Now if we simplify, we cancel out the dx's, we have the integral of 1 over gy dy equals the integral of fx dx. In that case, we've separated the variables. Example 15. Determine the general solution to the differential equation. So step 1, rewrite the differential by separating the variables. dy dx equals x squared over y squared. If we multiply both sides by y squared and then times both sides by dx, we now have y squared dy, x squared dx. We can go to step 2, which is integrating both sides. So the integral of y squared is with respect to y, and our x squared is with respect to x. So our y's with our y's, and our x's with our x's. These become really short integrals to complete because we use the power rule, which is y cubed over 3, x cubed over 3. We have a constants of integration. We can then rearrange this. If I wanted to then subtract the constant 1 from both sides. And really what we do then is that we have an answer here, which is y cubed over 3 equaling x cubed over 3 plus c, where c is your c2 minus your c1. Step 3, transpose, make y the subject. So we're making y the subject. I'm going to multiply both sides by 3. And then I'm going to take the cube root of both sides. Now I've made y the subject. Example 16. Solve the differential equation. Step 1 is to rewrite by separating the variables. So we're going to multiply both sides by this 2y take sine of y. Now if we look at it, we actually have our y with our dy and our function with x with our dx. So we can integrate both sides. So integrating both sides, our dy is with respect to our y's, our dx is with respect to x. We can integrate, which is now y squared. Integral of negative sine y is cos y. 9x squared becomes 9x cubed over 3, which is 3x cubed. Transpose and make y the subject. In this case, it's not possible to express y explicitly as a function of x. If you're trying to rearrange, we're not going to really be able to get y, as we say, as a subject all by itself because of this sort of equation. Example 17. Solve the following differential equation. Over here, I can see some initial conditions. That means when we solve this, we can get a particular solution. we have a dydx, we have e to the 5x, but we have our y's over here. Step 1 is to rewrite the differential by separating the variables. To do that, we could, instead of a subtract here, we could add this to both sides. So now we have dy dx equals e to the 5x multiplied by this function of y. I could then separate these further by dividing both sides by the function containing y, which is the root of 100 take y squared. I could then multiply both sides by dx. Now I have a function that is in terms of, we can integrate it in terms of y, and e to the 5x is with our dx. So step 2 is to integrate both sides. So I'm taking the integral of the left and right hand side. This one is, you've got to recall, is your inverse sign, because here our a value is 10. So it's 10 squared take y squared. So therefore it's the inverse sign of y over a, which is y over 10. In this case I've just written an arc sign. Here e to the 5x will then have our derivative of 5x, so we're dividing by that 5, and e to the 5x stays the same. Determine the constant of integration. So here we were told that when x equals 0, y equals 0. So we can sub in x equals 0 and our y equals 0. Now, the arc sign of 0 is 0, e to the 0 is 1, so it's 1/5, hence c is going to be negative 1/5. We can now transpose and make y the subject, now knowing that this c is negative 1/5. So c is negative 1/5, we've got to transpose and make y the subject. If we do that, what I've done is factorise the 1/5 out, so 1/5 outside of e to the 5x take 1. Next, of the inverse of your sign, then is sine, the sine of this function of x. Lastly, multiply both sides by 10. We now have y as the subject. Example 18. Solve the following differential equation where initial conditions where x equals 0, y equals 1. So step 1 is to rewrite the differential by separating the variables. So this first case, we've got just rewritten the differential. If we now rewrite this by multiplying both sides by the e to the negative x squared, y squared take 1, I've now got that with my dy. I've then still got this negative xy, but I've brought the dx over. The problem here is that we need to rid the right hand side of y. So to do that, we're going to multiply both sides by e to the x squared over y. If I do that, I'm going to multiply left hand side by e to the x squared over y and e to the x squared over y. So what's going to happen here is you've got your e to the x squared and your e to the negative x squared. And by doing so, you would have e to the 0, which is 1. So now I'd have the y squared take 1 over the y in terms of dy. Here, the y's are going to cancel out, and I'm left with negative x e to the x squared dx. Now we can go to step 3, which is to then integrate both sides. But to simplify it a little bit further, I divided y squared by y, which is y. Negative 1 divided by y is negative 1 over y. That's going to help us integrate later. Step 3 is to integrate both sides. The left-hand side is quite simple to differentiate because that's going to become half y squared. This will become a natural log. The right-hand side, we're going to have to use a substitution method. So to refresh your memories, if you let u equal x squared, du dx then is 2x. And if I write dx as the subject, we have du over 2x. I can now rewrite this integrand in terms of pretty much u. In that case, I'll then have negative 1/2 the integral of e to the u, which will simply be negative 1/2 e to the u, where u equals x squared. The next case is to determine the constant of integration, where x was 0 and y was 1. If I use my calculator to evaluate, c miraculously equals the number 1. Now we can go to step 5, which is to express the implicit solution, in this case still in implicit form. So we have our solution. We multiply both sides by 2. We'll have y squared take 2 lots of the natural log of y equals negative 1 e to the x squared plus 2. Here we can't really do a heap more apart from rearranging a little bit more, which is having y squared take 2 ln y plus e to the x squared equals 2. And that's our implicit solution.